Okay. So yeah, 8:35. So yeah, everybody should have handed in their assignment 3. I will post the solutions sometime today. I have a bunch of stuff to do, but assignment 4 is not quite out yet. It's there's a version that we're looking over. Will probably be released either today or tomorrow. Yeah. 7D. Yeah, I can. Sure, why not? So let's. Yeah, but first of all, any other questions on the schedule or anything like that? Okay, so 7D. I will try and do it from memory here. So we had 100 snakes, and the snakes are basically a stand-in for a permutation, right? So if you think, so a snake 1 biting snake 2's tail, you can think of it as snake 1 takes snake 2's position in the permutation. All right, so the initial hint is, well, of course, how many different permutations of 100 snakes are there? Well, that would be our sample space, and that is 100 factorial, right? It's just all the permutations of the snakes. And then the previous part C, asked you to compute the probability that all the snakes formed a big cycle. All right, so let's talk briefly about what that means. So let's take a small set of numbers, 1 through 5, and then I do some permutation. I do 2, 1, 3, 5, 4. Okay, that's a permutation, and this permutation has 3 cycles, right? So the one cycle is that 1 goes to 2 and 2 goes to 1. The other cycle is 3 goes to itself, and the other cycle is 4 goes to 5 and 5 goes to 4. Okay. Now, if we can have a cycle of all of these numbers, so I mean, one easy way to do that. Let's start again with these. One easy way to do that is just to shift all the numbers to the right, for instance. Right, so 5 will come to the front, 3, 4. And that's a cycle on all the numbers because 1 went to 2, 2 went to 3, 3 went to 4, 4 went to 5, and 5 came back to 1. Okay, so that's when we talk about 100 snakes in a cycle, we mean something like that. And the big hint, I gave you the sequence of tasks, and then you had to sort of count them, and hopefully that gave you an idea of what we meant by the cycle and how to compute it for other sizes. Okay, and so the sequence of tasks, if I wanted to figure out, again, okay, my eraser doesn't work, neither does Outlook or OneNote. Okay, give me a second. Perfect, all right, wow. Okay, so 100 factorial is the size of my sample space, but let's look at, again, let's look at the smaller version and say, okay, well, how many different cycles can I have on these 5? Well, I'm going to define a sequence of tasks. The sequence of tasks is I'm going to start with snake 1. Task 1 is decide who snake 1 bites. Okay, and there are 4 possibilities here. So let's say I mapped snake 1 to snake 3. Now I continue with snake 3, task 2. This is task 1. Task 2 is I take snake 3 and decide who snake 3 bites. Well, I don't want to close. Again, I'm trying to count the number of cycles on all 5 of these snakes. I don't want to close it early. So snake 3 cannot move to its own position because 1 is already in its position, which corresponds to, snake 3 biting its own tail after 1 has already bitten its tail. And it can't go back to 1's position because that closes the cycle early, right? Then we just have a cycle on 1 and 3. So number 3, I'm going to pick something else, maybe 5. So 3 bites 5. But in particular, 3 has 3 choices at that point. Can't bite its own, it can't bite the first one. And then task 3, snake 5 bites snake 4. But again, snake 5 only has 2 choices. So whatever, snake 5 bites somebody, but there's 2 choices. Snake 4 can bite only snake 2. I can't bite snake 1 yet because snake 1 is the last snake to be bitten to form a cycle. So task 4 is we have 1 choice. And then task 5 is we complete the cycle, snake 2 bites snake 1. And there's only 1 choice for that as well. So then, and I think many of you got this. So for my 5 snake examples, the probability that they form a big cycle is 4 factorial over 5 factorial, which is 1 over 5. For our 100 snakes, we had a similar setup, except, you know, the number of ways we could form 1 big cycle is 99 factorial. That was over 100 factorial, and if you cancel everything out, you get 1 over 100. Okay, so that's part C. And you have to, you know, it really helps to understand that, all of that stuff before you move to part D. And then part D, we're going to say, so D is that greater than 50 snakes in the largest cycle. Okay. So one thing to note is that if there's more than 50 snakes in the largest cycle, then the largest cycle is unique, right? I cannot have 2 large cycles of 51 because they're closed, right? So if I have a cycle of 51, the next biggest cycle I can have is 49, right? So the fact that there's greater than 50 snakes means that the largest cycle is unique and I don't have to worry too much about double counting things. Okay, so if I have 51 snakes and I'm going to take some permutation, but they're going to be in a cycle, 1 large cycle, then the number of ways in 1 large cycle, then the probability of that, the probability of the 51 snakes in 1 large cycle is 50 factorial over 51 factorial, right? So it's basically the same thing we did for the 100 snakes, 99 factorial over 100 factorial. Now it's 51 snakes. Of course, that's not all we have to count, right? We have to count, well, I have 100 snakes and I want to count the event that there's 51 snakes in the largest cycle. Well, first of all, I have to figure out which 51 snakes there are, right? So that's going to be, if I want let's call this event A, or let's call it event A51. Okay, that means there's 51 snakes in the largest cycle. So if I want to count this event, well, the first thing I want to do is choose 51 snakes out of 100. Okay. And then I'm going to, well, the number of ways that I can have them, the number of ways that those 51 snakes can be in a cycle is 50 factorial over 51 factorial. And then I have 49 snakes left, and I have to arrange those as well, but now I don't care. They can be in 1 large cycle or many individual cycles. So the number of ways for the rest of my snakes to be permuted throughout 49 locations is 49 factorial. Okay. Questions? Yeah. Yes, exactly. Yeah. There's only one way for them to do that. Okay. So I have now an expression for 51 snakes in the largest. Now I'm simply going to write that as a summation, right? So I can have either 51 snakes in the largest cycle, or I can have 52 snakes or 53 snakes. And these are disjoint sets, right? If I have 51 snakes in the largest cycle, I cannot also have 52 snakes. There's no intersection there. So that means I'm going to use the sum rule. So I can write this as I equals 51 to 100. I is the size of the largest cycle. 100, choose I. And then I minus 1 factorial over I factorial. And then times 100 minus I factorial. Right, so that's just, this is the general form of this formula here. Okay, so now I still have kind of a mess here, but there's a bunch of stuff that I can cancel out. In particular, if I expand my binomial coefficient, that expands to 100 factorial over 100 minus I factorial times I factorial. Right, and then that is times I minus 1 factorial over I factorial times 100 minus I factorial. Okay, so what I did is I just took this binomial coefficient and I expanded it out using this formula that we know. And then I could start canceling. So this 100 minus I factorial cancels out. I mess up somewhere? No, I think I'm okay. I may have messed up somewhere. I might have to go back to the, but let's continue. And so let me see here. I equals 51 to 100. 100 factorial. I have I minus 1 over I factorial. I might have screwed up somewhere, but let's keep going and see what oh, yeah. Sorry, I did mess up. So I'm conflating probabilities. So this is 50 factorial over 51 factorial is the probability that this happens. But yeah, but in terms of, sorry, yeah. So this is the probability, but in terms of counting, it's just 50 factorial, right? Yeah. Okay. So I slipped in a little probability into a pure counting. So here I just wanted to count the size of the set where I have 51 snakes in their own in the largest cycle. Okay, and then I threw that extra this in by mistake. Okay. Does it make sense? Questions on that? Yeah, okay. All right, so 50 factorial is the number of ways I can arrange my largest cycle. 49 factorial is the remaining snakes, how I can arrange them. And then, yeah, and then I can generalize it for I, and then my binomial coefficient. Yeah, so this cancels out with, so I minus 1 factorial cancels out with I factorial, and I get 100 factorial over I. And again, I'm just counting all of the ways. This is counting all of the ways that I can have greater than 50 snakes in my largest cycle. This is not yet a probability, right? So this is the size of my set, let's call it AL for largest cycle, right? So this is the size of my set. And now if I want to determine the probability, I want the size of this over the size of my sample space, which is this one here. So I had, I have I factorial and I minus 1 factorial. So I minus 1 factorial is 1 times 2 times 3 times 4 times up to I minus 1. And this is that times I, basically. Yeah. Okay. So yeah, now I have this sum I equals 51 to 100. 100 factorial over I over 100 factorial. The 100 factorials will cancel out, and it's left with 100. I equals 51 to 100 of 1 over I. And then that breaks down into the two harmonic numbers. I can write this as I equals 1 to 100. 1 over I minus I equals 1 to 50. 1 over I. And those are both the harmonic numbers, H100 and H50. All right, so questions? It was hard, but we wanted to throw something a little bit harder just to see who could get it. And hopefully you get at least part marks. This is actually part of a sort of a semi-famous problem. I'm not going to explain it in all its detail right here, but it is sort of remarkable. The actual problem is something to do with prisoners, and a bunch of prisoners. There's 100 prisoners, and then there's 100 boxes, and each prisoner can open 50 boxes. And if all the prisoners find their own name, then all the prisoners go free. And so that the probability of that happening is, if there's no strategy, then every prisoner has a probability 1/2 of finding their own name, and then that's 1/2 to the 100, which is almost nothing. But if they use this strategy, that, well, there might be no large cycles, right? If there's no large cycles, then they can use a strategy, and everybody can find their own name with a probability of like 30%, which is sort of remarkable. But yeah, it was based on that problem. All right, questions? Okay. All right, so infinite sample spaces, yes. Okay, so Rosencrantz and Guildenstern Are Dead is a play. I forget who wrote it. I don't know. I don't think that was Shakespeare, was it? Shakespeare wrote Hamlet, and then somebody else wrote this based on, there's these two comic relief characters in Hamlet. At the beginning of this play, they're flipping a coin, or rather, Guildenstern is flipping a coin, and it keeps coming up heads over and over and over again. For the entire first scene, as they're talking, this coin keeps coming up heads, and Guildenstern remarks, you know, a weaker man might be moved to re-examine his faith, if for nothing else, at least in the law of probability, right? Because if you flip a coin 100 times, for it to come up heads 100 times is extremely unlikely. Not impossible, but very, very unlikely. All right, and then eventually, at the end of the scene, there's an ominous moment where they talk about, I forget how it goes exactly, but they talk about death or something like that, and then it comes up tails, and it sort of signifies something. But the point of that is that he was performing an experiment where he's flipping a coin until it came up tails, right? And so we're going to look at similar experiments. Now, the difference between these experiments and the ones that we performed so far is that this has an infinite sample space, technically. I could flip that coin 1,000,000 times, and it could come up heads 1,000,000 times, or more than that, right? I don't know. So this is the idea behind infinite sample spaces. Right, so again, just a short review. A sample space is just a set of outcomes for my experiment. And each of those outcomes has a probability assigned to it by a probability function. Each of those probabilities must be a number between 0 and 1. And if I sum up all of the probabilities of each individual outcome, they should sum to 1. Okay, so up until now, all of our sample spaces has been finite sets. So it was sort of, easier to assign these probability functions, but we can have sample spaces that are infinite sets. And the first example we'll look at is the example we were just talking about. We take a fair coin, flip this coin until it comes up heads for the first time, right? So now I have a set of outcomes. Each of these coin flips are independent of the others, and it's a fair coin, so it's 0.5 probability for tails and 0.5 for heads. And now if I want to look at my sample space is a set, but now it's an infinite set. And it consists of, well, obviously, if I flip heads first, I'm done. Or maybe I flip tails and then heads. Or maybe I flip tails twice and then heads. These are all possible outcomes. And essentially, there's an infinite number of them, right? So n can be any number, 0 or more. I flip n tails and then heads, and that's a legitimate outcome in my sample space. Okay. So these flips are independent, and as we mentioned, when we have sort of these independent events, we can cheat a little bit determining their probability. In particular, the probability of the intersection of these events is equal to the product of the individual probabilities, right? So the probability that the first flip is tails, and the second flip is tails, and the nth flip is tails, and the nth plus 1 flip is heads, is equal to the probability, since they're independent, that the first flip is tails times the probability that the second flip is tails, times all the way up to the probability that the n plus first flip was heads. Okay. All right. So the probability of any given outcome where I have n coin flips that are tails and the final flip is heads is 1/2 to the n plus 1, right? Since it's a fair coin. Questions so far? Okay. So this is an infinite sample space, and we know that any sample space, all the probabilities must sum to 1, right? So we're going to, as a sanity check, we're going to verify that I can look at every single possible outcome, and I can take the sum of them, and that sum will be 1. Okay, which may seem a little bit counterintuitive, but so before we do that, we're going to learn about infinite series, or an infinite sequence, and then we're going to learn how we can find a closed form, right? So we've talked about closed forms before. For just a general series or sum, right? We can convert them sometimes into just an expression that doesn't have that sum. So that's what we want to do. We want to convert this infinite series into a closed form so we can actually compute some probabilities. So we're going to take an infinite sequence of numbers A0, A1, A2, and define the sum of these numbers this way. So if we have finite many numbers in this sum, we will use big N, and then we can just write it as the sum of n, small n equals 0 to big N of all of these numbers. Okay. We are actually going somewhere with this, but if we want to define it for infinity, right, we can write it as the limit as n goes to infinity of n equals 0, little n equals 0 to big N. And we write it like that because it might not be defined for n equals 0 to infinity, right? If I replace that with infinity, I might not get a number. So in order to keep things sort of grounded mathematically, this is how I would write it. And then later we'll prove that actually it does converge, which means it does have a sum if we go to infinity, and then we can get rid of this big N. Okay, so yeah, if the limit exists, then we can we can forego all of this extra machinery here and just write it as n equals 0 to infinity of an. All right. So this is what we do to hedge our bets. Once we're sure that it converges, we can write it like this. Okay, so now we're going to look at a series where we define each item in the sum as some x to the power n, where x is some value between 0 and 1. Okay, this is known as a geometric series. So yeah, then we can define this this summation from 0 to infinity using our big N just to sort of hedge our bets, because this is always well defined. This might not be, but we're going to prove that it is, basically. Okay, and the closed form, which I'm just going to give to you, and then we'll prove it after, is this, right? So if I have some summation, n equals 0 to big N of x to the power n, where again, x is a number between 0 and 1, then I can write that as this closed form. And then, I can tack this on, which does not really change the equality, because it's not actually going to infinity, it's as n approaches infinity. But yeah, so this is my claim that this is equal to this. So first we're going to prove that. It's not that hard, and then we'll go on. This is a geometric series, right? So if you look up geometric series on Wikipedia or something, it'll give you lots of good formulas and things like that. So yeah, we could prove this by induction on big N. However, we're just going to sort of do a little bit more of an informal approach. So if I take this summation and I expand it out, I get this, right? So x to the 0 is 1, x to the 1 is x, x to the 2 is x squared, and all the way up to x to the power n, right? So this summation here is exactly the same as that summation there. And then my claim is that it's equal to this. And so how I'm going to prove that is I'm going to multiply both sides by 1 minus x, and then show that this times 1 minus x is equal to 1 minus x to the power big N plus 1. Okay, so multiply left and right by 1 minus x, and I get this. Okay, and now what I'm going to do is multiply this entire series by 1, and then to that, I'm going to add negative x multiplied by that entire series. Okay, so I'm just going to sort of distribute this over my series here. Question so far? Okay. Okay, so what does that give me? Well, I'm going to take the left-hand side. Right. So if I take this one and multiply it times everything in the brackets, then I get this top of the left-hand side here, all the way up to x to the power n. And then added to that, I'm going to multiply every term by negative x. And that's where I get, so negative x times 1 is negative x. Negative x times x is negative x squared. Negative x cubed, etc., all the way to negative x times x to the power big N, which gives me negative x times x to the power big N plus 1. Okay, so this, what I've done is I've taken this left-hand side here, and I just expanded it out, and I drew it on 2 different lines, but that's it. Okay, so now what do? Well, we look for all these terms that are going to cancel each other out. So I have plus x here and minus x there, so they cancel each other out. I have plus x squared and minus x squared, so they cancel each other out. And so on, all the way down to x to the power big N minus x to the power big N. So all of these are equal to 0. All of that in middle stuff is equal to 0. And I'm left with 1 minus x to the big N plus 1. That's my left-hand side. And of course, you'll notice that it's also my right-hand side. Right? So that means that, yeah. So what I wanted to do is I wanted to take this and express it as a closed form of, let's see if I have a better summation of that. Yeah, basically I wanted to take this summation and express it as a closed form of this. I expanded it out. I multiplied both sides times 1 minus x, and then that kind of showed that they were equivalent after I canceled out all the stuff that added up to 0. Okay, questions? Okay, so now I have a closed form, and so I have a series, summation that I want to find a closed form for, and I have an equivalent series where n is finite, and I have a closed form for that, but I still want to get back to this, right? We are dealing with an infinite sample space, so I want to get rid of this big N here. So let's look at this a little bit deeper. So if I have my number x is between 0 and 1, that's a fraction. Every time I multiply it by itself, it gets a little bit smaller, regardless of what the number is. It can be 0.99999, but every time I multiply it by itself, it gets a little bit smaller. And so as big N goes to infinity, I multiply x times itself infinite number of times, and that goes to 0. Okay, so because x is between 0 and 1, the limit as big N goes to infinity of x to the power big N, or big N plus 1, is 0. Which means now I have this closed form here is equivalent to this. The limit as n goes to infinity is 1 over 1 minus x, which means that I finally have a closed form for my geometric series here. Okay, so I'm looking for a tool to sum up all of the probabilities in my infinite sample space. And so I'm looking at this geometric series here, and we've proven that we have a closed form, 1 over 1 minus x. And this is the tool we're going to use to sum up our sample space. Okay. Right, so we can test this out for x is equal to 2. This has nothing to do with our sample space. We're just going to do sort of a sanity check on this closed form that we developed. So let's take x equal to 1/2. The closed form, so if I expand this out as an infinite series, I get 1 plus 1/2 plus 1/4 plus 1/8, right? What we really want to show here is this converges, right? So if x was not between 0 and 1, then this infinite sum would never, it wouldn't have a limit as x goes to infinity. It would just keep growing. But because x is between 0 and 1, we do have a limit, and we sort of want to try and convince ourselves that we found the accurate limit. So 1 plus 1/2 plus 1/4 plus 1/8, all the way up to infinity, is equal to 1 over 1 minus 1/2, which is equal to 2. And we can, so this is not a proof, but we can visually see this. I can make a number line between 0 and 2, and then, well, I'm going to start by adding 1. So if I add 1, that means I'm going to take this much here. And then to that, I'm going to add 1/2. And you'll notice that, well, I'm going to add this much here. You can also sort of think of it as I start at 0, I go halfway to 2, and then I'm at 1, and then from 1, I go halfway to 2 again, and then I'm at 1.5, and then from there, I'll go halfway to 2 again, and then I'm at 1 3/4, and then I keep going halfway closer to 2, up to infinity, right? So I always only get halfway closer to 2, so I never actually reach it, but in the limit, it's equal to 2. Okay. Any questions? All right. Okay, so back to our problem of infinite sample spaces. We want to show that the probabilities in our sample space will all sum to 1, and we're going to use this closed form of a geometric series. So we know that any given outcome, right, I flip tails n times and heads once, has a probability 1/2 to the n plus 1. And I have infinite number of those. So I'm going to sum all of these from n equals 0 to infinity. So yeah, I get this expression here. Hopefully that's pretty straightforward. Now we want to, this is not quite in the form that we want. We want something that looks like this. So we have n equals 0 to infinity, but we have an n plus 1 instead of an n. So we're going to get rid of that n plus 1 and make it look like this thing. So what we're going to do is we're just going to factor that out, right? So this is 1/2 times itself n plus 1 times. Every single term in this series has a factor of 1/2 that we can extract. So we're going to extract it and bring it out front. Okay. And then we have n equals 0 to infinity, 1/2 to the power n, which now is in a form that we can use. So we can plug in our closed form. I get 1/2. This is my 1 over 1 minus x is this part. Right? That gives us 2, the same as we got before. But now I have to multiply that by this 1/2. So I get 1/2 times 2 equals 1. So indeed, when I sum up my infinite sample space, the probabilities sum to 1 as they should. All right, questions? Okay, so for infinite sample spaces, I mean, this is your most useful tool, right, to compute them. How are we doing? 9:15, right. No, yeah, and there's, I mean, I have a few slides on sort of alternate ways that get you to the same answer, right? Since, yeah, I can expand this out using the fact that these are independent coin flips. I can expand this out into the probability of getting tails times itself n times the probability of heads. And then I can take the probability of heads out since it appears in every term. And then I have n equals 0 to infinity of the probability of tails to the power n, and I get the same answer. And I think I might do one more here, but we will skip that one. Oh yeah, you can see if you look at the individual terms, then you get this series 1/2 plus 1/4 plus 1/8 plus 1/16, which you can kind of convince yourself sums to 1. I'll leave that as an exercise for you guys. But yeah, all right, questions so far? Yeah. Sorry?
So I noticed that I could see the coin flip, tails and tails are related with skip lists.
Yes. Yes, they are. It's the height of your skip list. That's yeah.
So because n goes to infinity and n goes to infinity.
Yeah, yeah. Did you take that in 2402? Oh, right now. Oh, okay, cool, cool. Okay. All right, so let's try and solve an actual problem, although a very simple one. So we're going to take a game, we're going to take a fair coin, and we're going to have two players, P1 and P2, and they're going to take turns flipping the coin until it comes up heads. And basically the first player to flip heads wins, right? So, yeah. So player one flips first, they get tails. Player two flips seconds, they get tails. Player one flips third, they get tails. Player two flips fourth, they get heads. Player two wins. Okay, so that's the game. It's kind of simple and not really that fair. Who do we expect to win most of the time in this game? Does everybody understand the game? Yeah, that's it. Of course, yeah, yeah. No, it's good. It's good textbook. Okay, okay. All right. Cool. So, okay, so I start flipping the coin. If I flip heads, I win. If I flip tails, it goes to you. If you flip heads, you win. If you flip tails, it comes back to me. So who is more likely to win in this scenario? Player one or player two? Yeah. Yeah, player one, right? Player one has at least a 50% chance of winning because they have a 50% chance of winning on the first flip, right? Yeah, exactly. Yes. At least that though, because they can win on a later flip. So it's going to be, we know immediately it's going to be more than half. So yeah, player one has the advantage in this game. All right. So we look at the sample space. The sample space is the same as the sample space we just looked at, right? Basically, I'm flipping a coin until heads comes up. And whoever made that flip is the winner. But in terms of the outcomes are exactly the same as what we just looked at. Okay, so now we're going to define an event A. An event A is that player one wins the game. Okay, so now we want to find the probability of A, of course. To find the probability of A, we're going to have to look at what outcomes does A contain. And A contains the following outcomes or the following subset of S. It's S, these outcomes where N is an even number, right? So if N is 0, that means player one wins. They got heads on the first flip. If N equals 2, then player one wins because they get heads on the third flip. If N equals 4, player one wins because they got heads on the fifth flip, and so on up to infinity. Okay, so everywhere that N is an even number is one of the outcomes in my event A. And they would all look something like this. But then I can express it a little more succinctly. If I know T is raised to an even number, well, I take an integer M, that's at least 0, and I multiply it by 2, and I get all of the even numbers. Okay, so this is what my event looks like, but I can express it this way. Okay. So yeah, this is not a uniform probability space. So we're going to go back to our old school definition of probability. The probability of my event A is simply the sum of the probabilities of each individual outcome in that event, right? So we're going to look at the probability of every outcome that looks like this, and we're going to sum them all together. And yeah, and of course, there's an infinite number of outcomes in this event. Okay. So each coin flip is independent, of course. So if I have the probability of, all of these events happening in succession, then because they're independent, this is equal to the product of their individual probabilities, right? So I have this is equal to probability that I flip tails times the probability that I flip tails And the probability that I flip tails 2m times, and then times the probability that I flip heads. So I get something that looks like this, right? So if I look at all of the times that I flip tails, there are 2m of them, and then the final flip is heads. I know each of these has probability 1/2 because it's a fair coin. So now I have m equals 0 to infinity of 1/2 to the 2m plus 1. This is my probability of A. Okay. So what we want to do is we want to take this. We do want to find a closed form for it. So we're going to use our famous tool here. But first, we want to make this 2m plus 1 into something that looks like this. So what we're going to do is, well, the plus 1, we've seen how to deal with that, right? That's an extra factor of 1/2 that occurs in every term, so we can take that out. And basically take it out of the summation altogether. And then what we're going to do is, all right, so let me draw this out a little more explicitly. So I take the 1/2 out of my summation, and I'm still left with 1/2 to the 2m. What I'm going to do then is, well, if I expand that out, I can say this is equal to 1/2 times 1/2 times 1/2 times 1/2, etc. And there are 2m of these. And then I'm just going to group every pair, every consecutive pair together, right? So if I did something like this, then now there are m of these terms, right? And I can do this because they're all multiplied together, so I can sort of evaluate this in any order that I like. So I'm going to take this 1/2 to the 2m, and I'm going to say that is the same as 1/2 times 1/2 to the power m. Okay. Okay. And 1/2 times 1/2 is 1/4, and we have to the power m, and I have m equals 0 to infinity, some number between 0 and 1 to the power m. So it's in exactly the form that I need in order to use my closed form. So now this is 1/2, and my 1 over 1 minus x is 1 over 1 minus 1/4. That is equal to 1/2. This part is equal to 1 over 3/4. I can invert that into 4/3. And then the 2's cancel out, and I get 2/3. All right, and let's clean that up a little. Yeah. Okay, so yeah, I basically took a subset of the sample space. It's my event A. It has an infinite number of outcomes. And to begin with, I had something that didn't quite look like this, but I used a little bit of algebra, and I made it so that it was in the correct form. And then I can apply my closed form and get the answer. And I get a nice, clean answer, probability 2/3 that player 1 wins. Questions? Yep.
So, and there's this next something. I think there's another one that I saw on the Wikipedia.
The which one? Okay, I don't know that off the top of my head, but
useful in the street structures.
Okay. I'll look it up if I yeah. Okay, so we have 2/3. What's the probability that player 2 wins? So, right, probability that player 1 wins is 2/3. So what's the probability that player 2 wins? Yeah. Yeah, it's 1/3 using the complement rule, right? So we did a lot of work to get to here, but we didn't have to do that much to get to player 2 wins, right? These are really, I can divide my entire sample space into either player 1 wins or player 2 wins. So together they have to sum to 1. But we can do the same process just as a sanity check, right? So the probability that player 2 wins is the same as the probability that I flip tails an odd number of times. So to express that, I take an integer m, I multiply by 2, I get an even number, I add 1, and now it's an odd number. Okay, so then I can, again, use the fact that these are independent, so I can, express each as the product of their individual probabilities. So I get 1/2 times 2 to the m plus 1 plus another one for my h here. So I get 2 to the m plus 2. And then I can go through the same steps. I have something that is close to what I want, this closed form here. I just have to make it into that. I can take this plus 2, that's 1/2 squared. That's a constant. I can move that out. It is equal to 1/4. And then I have this 1/2 to the 2m. We already know how to solve that, right? We can group those halves together, so they are 1/4 to the m. And then I can plug in my closed form here and multiply that times 1/4. And I get 1/4 times 4/3 or 1/3. So I didn't have to do that, but for this nice simple example, it's at least good to do it at least once to verify that this all works. So yeah. Okay. All right, let's take it a step further. We're gonna skip this stuff. We're gonna go to an easier version. So this is basically, I have a new game. The new game is player 1 and player 2 take turns flipping the coin, and the second player to flip heads wins. Okay, so now I have a similar sample space, not quite the same, because the first player to flip heads, that does not stop the game. The second player to flip heads, that's what stops the game now. And what we can do, right, so the sample space of that is, of course, something that looks like this, right? So I flip n number of tails for some n at least 0, followed by heads, followed by m number of tails for some m at least 0, followed by heads. So it's an infinite sample space, but now it's a little bit trickier because I have to account for what are these values n and m. And I have, at least 2 heads. Okay, so that is the new game, and you can solve it using the same technique as we used in the old game, right? I can simply, do exactly what I did before. I'm going to get some expression 1/2 times to some exponent, and then I can massage that and get, but now I'm going to have 2 variables, n and m, but that doesn't change it that much. But we're going to do something else instead. We're going to look at arguably an easier way to solve this. Okay, so this is the same game. We're flipping a coin. The second player to flip heads now wins. So we're going to say that this game now, in some sense, is 2 individual games, right? So I have one game until the first player flips heads. And then I follow that by a second game where the next player flips heads. Okay, so instead of taking it as a whole, I'm going to break it into two sort of separate events. And we can describe these events using this notation. So I have I and j where I can be 1 or 2 and j can be 1 or 2. This is the players. And so event Bij is this event that player I starts the game, right? Player I is the first one to flip. And then player J wins the game. And it could be that I and J are the same. For instance, the event B11 is that player 1 starts the game and player 1 wins the game. And B22 is that player 2 starts the game and player 2 wins the game, right? And these both have probability 2/3 because in the previous section, we proved that whoever starts the game has probability 2/3 of winning the game, okay? In addition to that, we also saw that whoever doesn't start the game has probability 1/3 of winning the game. So I have an event B12 is player 1 starts the game or starts that round of the game and player 2 wins. And I have another event B21 where player 2 starts the game and player 1 wins, right? Or game or round or what have you. And we know that has probability 1/3. So we're going to use that stuff that we already know, and then we're going to, sort of paste these events together. Okay, so second player to flip heads wins, and we want to define the event A is player 1 wins, and we're going to, hopefully this is a slightly easier way to figure out the probability of A. And what we're going to do is, so this is our sample space, of course, but we can also express any of these strings by some concatenation of these strings, right? So each of these events represents a sort of a substring. So we can concatenate these substrings together and get every possible string in our sample space. So for instance, so I have 2 rounds now. Round 1 ends when the first head is flipped, and round 2 ends when the second head is flipped. And I know that whoever wins round 1, right, the other person starts round 2, right? Because we keep switching until the second heads comes up. So for player 1 to win, it can happen all of the outcomes can be sort of described using this notation of substrings where player 1 wins the first round and player 1 wins the second round, or player 1 wins the first round and player 2 wins the second round, player 2 wins the first round and player 1 wins the second round, or player 2 wins the first round and player 2 wins the second round. So those are all of the possibilities, right? That this sort of informally represents everything in our sample space. And we can express the event A is player 1 wins as the union of these 2 events. Okay, and those 2 events we can express as using these events. So event A, player 1 wins, is player 1 wins the first round and wins the second round, or player 2 wins the first round and player 1 wins the second round. Okay. All right, so yeah. That's a problem with slides. Sometimes I explain things in a different order than the slides does things, but okay, so let's go back to the slides. So I'm going to split this event A, player 1 wins, into 2 disjoint subsets, right? So if I look at all of my outcomes, some of the outcomes where player 1 wins the game, player 1 also wins the first round. Some of the outcomes where player 1 wins the game is that player 2 wins the first round. So then this event, player 1 wins, if and only if player one wins the first round and the second round, or player two wins the first round and player one wins the second round. Right? So these are disjoint subsets that completely describe this set A. And since they're disjoint, we can use the sum rule. Right? So my probability that player one wins is the probability that player one wins both rounds, plus the probability that player one only wins the second round. And then, as mentioned before, these events represent a string, and I can, in some sense, break that into two substrings. Yeah.
Yeah, but I think those I see as a probability. Yeah. You can sort the windows within the matrix.
Yep. Yeah, you can definitely do that. Yeah. You can, oops. All right, one sec. Yeah, you can draw it, yeah, you can draw a little square, the 4 squares and 4 outcomes. Yeah.
Square matrix.
Yeah, yes. You can do 1, 2, 1, 2, and then put all the probabilities. Yeah. Yeah. Okay. I think I did a typo here. Oh no, sorry. Yeah. So A1 is player one wins the first round and second round. And then I can look at that as player one. I know player one starts the first round. And then I know that player one wins the first round. And because player one wins the first round, player two starts the second round, and then player one wins the second round. All right, so if I divide it into those two substrings, the first substring is B11, right? Player one starts the first and wins the first round. And then that's concatenated with this substring B21, this event B21, where player two starts the second round and player one wins the second round. Okay. So I can look at A1 as event B11 and B21 both happening. And I can express it using this logical AND. Okay, so what is the probability of B11 and B22 both happening? So I'm going to kind of informally give you a technique that nonetheless works, rather than getting into the law, law of total probability. So we're going to skip that. We're going to go with sort of an intuitive understanding of this, right? So the intuitive understanding is that, well, you can ask yourself, are these two events independent? And in some sense, they're not, right? Because this event can only happen if player one wins the first round, right? So they're not really independent. You should be using the law of total probability, which states something along the lines of probability of B21 given that B11 happened times the probability of B11. This is the way you should do it, and this is the law of total probability, which we didn't really cover. I might cover that at some point. But the probability that player two starts the first round and wins the second round, given that, or sorry, player two starts the first round and player one wins the second round, given that player one won the first round. Well, all the coin flips are independent. So that means that is simply equal to the probability of B21 and then times the probability of B11. So that is how you should do it. But intuitively, we can sort of understand that, yes, B21 only happens if B11 happens, but all the coin flips are independent, which means that if I know that both of these events happened, then the probability that they both happened is equal to the product of their individual probabilities, right? Hopefully that makes some sort of sense. So yeah, my probability of A1 is probability of B11 times the probability of B21, which is 2/3 times 1/3, which is 2/9. All right, questions? All right. We can do the same thing for A2. A2 I can split into two events, B12 followed by B11. And again, I'm just taking this string and I'm splitting it in two. And because there are no coin flips in common between these two substrings, they're independent. So I can express the probability of A2 as the intersection of these two, and I can simply multiply the individual probabilities together. Yeah, so I get 2/3 times 1/3 is 2/9. Right? Hopefully that's sort of clear. So A2 is, yeah, I can look at A2. So let's say one of the outcomes of A2 is player one starts. I get tails, heads, right? This is my B12, and then followed by, well, player one starts again, tails, 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 heads. Yeah. And this is B11. So this little string is one of the outcomes in A2, and I'm simply splitting it into two substrings. Right? And since those two substrings don't have any flips in common, their probabilities are independent. Okay. Arguably easier than the other way. Easier once you understand it. The other way, you can also do this the other way that we did the first time. So I have probability of A1 is equal to 2/9. My probability of A2 is equal to 2/9. My probability of A, since these are disjoint subsets, I'm going to use the sum rule of probability. So I get the probability that player one wins is 4/9. So yeah. So if we, break it down into now the second player that flips heads wins. Now player one has the disadvantage, right? So 4/9 is less than 1/2 in this case. So the probability that player one wins is 4/9, and the probability that player two wins is 5/9. You can keep going. Yeah, questions? Okay. So yeah, the real idea is that when you have these infinite sample spaces, you can break them down into, in some sense, substrings. And then you can use the fact that they're independent to, it's an easier way to find the probability of these events. And yeah, we can do the third player to flip heads wins. We can sort of extend that very, very quickly, right? So my event A is that player one wins, and I can break it into sub-events depending on who wins the first and second games. As long as player one starts the first game and player one finishes or wins the last game, then I can, I can express all of the outcomes as the intersection of these three events. Right? And then, well, you can figure out exactly how many of these intersections go into this. Yeah, so we can divide A now into 4 different subsets and express each as the intersection of some of these events. And then you can quite easily, again, you're going to use the fact that these are independent. So you're going to take the product of these individual probabilities. That's the probability of A1. Product of these individual probabilities is the probability of A2, etc. And then I'm going to use the sum rule to add up all of these individual probabilities and get the probability A that player one wins on the third the third head that comes up. Right, so very, very quickly, probability of A1 is 2/27, probability of A2 is 2/27, A3 is 2/27, and A4 is 8/27. And if you sum all those up, you get on the third coin flip, player one wins with probability 14/27. All right, and you can keep going and it will get closer and closer to 0.5, but always the person, yeah, when it's a even number of heads, the person that starts has a disadvantage. When it's an odd number of heads, the person that starts has the advantage, so to speak. All right. I think we could do, yeah, 10 minutes. Questions on that? All right, let's do an easier one. We'll do craps. This is sort of a more straightforward, similar to the first example, but a little slightly more involved. So craps is a game, you roll 2 dice, you bet on the outcome. Again, I don't recommend playing it. But the probabilities are rather sort of straightforward to compute in gambling because they're made to be random. So in craps, you roll the dice, and if you roll a 9 on your come out roll, as it's called, then you have, now your mission is you keep rolling the dice, and if you roll, what is it, a 7, you lose, right? House wins. If you roll a 9 again, then you win. All right, so you have your come out roll, and there's certain rules, and then people make a bunch of side bets and whatever, but basically you roll some number, and then you have to roll that number again before you roll a 7, and that's how you win. So in this scenario, we're going to assume that we rolled a 9 on the come out roll. Now we want to find the probability that we win, which is the probability that we roll a 9 before we roll a 7. Okay. So we need to determine, well, we have a bunch of die rolls, they're all independent, but we need to know the probabilities of those individual die rolls. So we want the probability that a single die roll, the probability that we get a 9, and we also want to know the probability that we get a 7, right? So these are our 7 is lose, 9 is win. And then, whoops, we can figure out the probability that we roll neither a 7 or a 9, and in that case, the game keeps going. All right. So R9 will be the event that we roll a 9 on a single die roll. R7 is the event that we roll a 7 on a single die roll. So the probability of R9 is simply, the dice are fair. So this is a uniform sample space. So it's simply the size of the size of our event that we roll a 9 over the size of the sample space. It's 2 dice, so the sample space has size 36. And if we look at all of the outcomes where we roll a 9, we can basically just count them in a rather, straightforward manner. There are 4 possible ways to roll 9 on 2 dice. So my probability that I roll a 9 is 4/36 or 1/9. That's sort of pretty straightforward, I think. Yeah. It's a casino game. I don't recommend gambling, seriously. I've had a lot of sad nights with friends who did dumb things like bet their rent money. Oh, seriously, it's not good. But it's fun to analyze, right? You can see how the house always wins. If you're going to gamble with friends, then that won't take all of your money. All right. R7 is the event that we roll a 7 on a single roll. Again, uniform probability. We're simply going to count the size of that set over the size of the sample space. R7 has 6 possible outcomes, right, where I roll a 7. So my probability that I roll a 7 is 1/6. Lastly, I need the probability that I roll neither a 7 or a 9. I can take that as using the complement rule is 1 minus the probability. that I don't not roll 7 or 9. Right? So we're getting sort of a double negative here, but of course the double negatives cancel themselves out. So I get 1 minus the probability that I rolled a 7 or I rolled a 9. These are disjoint, so we can just use the sum rule. Oops. So yeah, it's 1. The probability that I didn't roll a 7 or a 9 is, of course, 1 minus the probability that I rolled a 7 minus the probability that I rolled a 9, right? So I just have these 3 disjoint events that completely describe my sample space. So this is 1 minus 1/6 minus 1/9, or 13 over 18. So this is a probability that I don't roll a 7 or a 9 and the game keeps going. Okay, so I have my 3 probabilities for any single die roll, right? Game keeps going, I lose, I win. Now I can roll the dice until I either lose or win. So we can write the probability that I win as I have some number of die rolls, maybe 0, maybe infinity, where I do not roll a 7 and I do not roll a 9. And then times the probability that I roll a 9 on my final die roll. Okay, so I know all of these individual probabilities. I know that each die roll is independent, so I can express this as the product of all of these individual probabilities. They have probability 13 over 18, and I do that I times, and then I roll a 9 with probability 1 over 9. Okay, and we've seen expressions similar to this before. This is already in a nice form. I have I equals 0 to infinity of something raised to the power I, and I have a constant that I can simply bring out of my, I can bring out of my summation, and then I can convert this to a closed form using my 1 over 1 minus x, which I don't have written out here, but I should. Right? I equals 0 to infinity, x to the I equals 1 over 1 minus x. So I can write that as 1 over 1 minus 13 over 18, and then times this 1 over 9. And I get a little bit of algebra, I get 2/5. Okay, so if I get a 9 on my come out roll in craps, the probability that I win is 2/5, less than a half. So yeah, don't gamble. Questions? Unless you gamble with friends, then it can be kind of fun. People still get mad. All right. Of course, we can use the complement rule to determine the probability that we lose. We can also compute it directly using the exact same process, but now instead of 1/9, instead of multiplying by 1/9, we're multiplying by 1/6, and we get 3/5. That's the house wins. Okay, so that is slightly more complicated than, or maybe not. But yeah, so that's 3 different versions of infinite sample spaces. Any questions? Okay, that's it for today. See you guys on Wednesday.